Being number 1 and number 1, A and B, and I'm starting with letter C here. Okay, letter C is an equilibrium problem. So anyway, letter C says write the expression for the equilibrium constant Kc for the reaction. Okay, so when writing the equilibrium constant, the expression, so you go Kc and it's equal, so it's always the products, and so this case it's going to be isobutane. And because they're isomers, they have the same formula, so you're just going to have to write the name. So isobutane, and it's to the first power, so it's because it's like C4H10 to C4H10, so it's just isobutane over N-butane. Okay, that's what your expression would be. Okay, now letter D says calculate the initial pressure in the container when the N-butane is first introduced before the reaction starts. So they give us some gas law data up here, so you can see that you could use P equals nRT and just solve that P will be equal to nRT over V. So P will be equal, if you plug in everything right here that you're putting in, 0.010 moles times R, 0.0821 atmospheres times liters divided by moles Kelvin times our temperature, but it has to be in Kelvin, so you got to take 25 plus 273, so that's 298 kelvins. And then we're going to divide that by the volume, and it's 1.0 liters. And so the pressure that we end up getting to start with is 0.24 atmospheres. Okay, so that's before it reaches equilibrium. Okay, so now let's go on to the next page here. Alright, so let's see here. Next page. Alright, so the N-butane reacts until equilibrium has been established. Calculate the total pressure in the container at equilibrium. Justify your answer. Well, notice how for every 1 mole of butane will turn into 1 mole of isobutane. So at equilibrium, when we had 0.24 atmospheres to begin with, when we had 0.24 atmospheres here, it doesn't really matter how the equilibrium shifts. The pressure is not going to change because it's a 1-to-1 mole ratio. You're going to have the same number of particles no matter what. So the total pressure isn't going to change at equilibrium. Okay? Alright, number 2. Calculate the molar concentration of each species at equilibrium. Okay, and if we go back and look, they gave us the Kc value as 2.5. Alright, so that's going to be important, so let's write that over here, that Kc equals 2.5. Now, a lot of times on the AP test they're going to give you this equilibrium constant, but they're not going to give you the concentration at equilibrium. That means that you should probably make an ICE table. So what we have is we have initial, change, equilibrium. Alright, so anyway, we'll draw that. This is supposed to be a C, not an E, but initial, change, equilibrium. Okay, so now we know from the beginning of this problem that we started off with 0.010 molar because if you read the problem, so we can go back and look at it real quick if you want. Okay, they gave us that we had 0.010 moles in 1 liter. So if you take the moles divided by the liters, that's going to give us our initial concentration of 0.010 molar. Now, what's going to happen is it's going to change by minus x. Okay, we don't know what that number is right now. Okay, so we know at equilibrium we're going to have 0.010 minus x, or minus x, not m. Okay, minus x at equilibrium. Alright, now initially the isobutane is 0. Okay, because it's a 1-to-1 mole ratio, if this goes down by x, this is going to have to go up by plus x. So at equilibrium we have x. Alright, now what we can do is we can plug these in to our equilibrium expression that we had written before, which was isobutane over N-butane. We can plug in our numbers. And so we know that Kc is 2.5, and that's equal to iso, which is x, over N-butane, which is 0.010 minus x. Okay? So then if we take this 0.010 minus x and put it over here with a 2.5, we're going to get 0.025 minus 2.5x. That's going to be equal to x. And then if we move the x's all to the other side, we're going to get 3.5x is going to be equal to 0.025. So x is going to equal 0.0071 molar. Alright? And so, at equilibrium, we know that our isobutane is 0.0071 molar. That's the iso. And then the N-butane, we would have to take 0.010 minus x, which we determined to be 0.0071, and that's going to equal 0.0029 molar. 0.0029 molar. So at equilibrium, for the N-butane we have that, and for the isobutane we have that. Okay, now letter 3, if the volume of the system is reduced to half its original volume, what will be the new concentration of N-butane B? Okay, well, we know that, if I do that up here, we know that right now at equilibrium we have 0.0029, okay, over 1 liter, okay. Now if we just cut that in half, that's going to be 0.0029 divided by 0.5 liters. So we've cut the volume in half. So that's going to equal 0.0058 liters. Now, since this ratio is 1 to 1, changing the volume will not require a shift in equilibrium. So cutting the volume in half will just double the concentration. That's what we ended up with there. Okay, and then letter 3, if the volume of the system is, no, not this one, wrong page. I need to go to the next page. Okay, suppose in another experiment 0.010 moles of isobutane is placed in the evacuated 1 liter cylinder and come to equilibrium at 25. Okay, so this one is just the reverse of the other reaction. So if you go back and look, this is just starting out with, instead of N-butane, we're starting out with isobutane. Well, since we're at the same temperature and the same conditions, the same amount, it's not really going to change the concentration because the equilibrium constant is going to be the same no matter which way the reaction is going. Okay? So it should be the same as before. Okay? That's it for this one.